Good morning everyone. I am Dr. Pravat Pati, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, I am going to discuss about the subject thermal engineering. So, this is a fifth semester course. This is a UG20 course, thermal engineering. So, what is the objective of this course? The usage of fundamental knowledge on thermodynamic cycles and fluid dynamics phenomena to present in turbo machinery and combustion for producing electrical and mechanical power. So, what the students will try to know about this subject after completing these subjects. Next, the operational concepts, principles, features, procedures, and detailed thermodynamic analysis related to components of power cycles, rocket propulsions, as well as steam and power generators. Right. The design approaches for developing governing equations and correlations related to intricate parts of turbo machinery and their components with the consideration of effect on the performance. So this is the third objective. And fourth one is a real world engineering problems and examples towards gaining the experience for designing and developing power generating systems in engineering practice. So these are the four course objectives what the student will try to learn after the completing of this course. Now, the today's topic is steam nozzles. So, what is steam nozzle? If you see the steam nozzle, a steam nozzle is a passage of varying cross sections, right? So, it is like a duct, right? It is a varying cross sections which convert heat energy of steam into kinetic energy. So, during the first part of the nozzle, steam increases its velocity, but in later part, the steam gains more in volume than the velocity. Since the mass of steam passing through any section of the nozzle remains constant, so the variation of steam pressure, right, in the nozzle depends upon the velocity and specific volume and also the dryness fraction of the steams. So, a well-designed nozzle converts this heat energy of steam into kinetic energy with a minimum loss. So, this is the working principle of steam nozzle. So, the main use of steam nozzle in steam turbine is to produce the jet of steam with a very high velocity, right? So this is the main function of steam nozzles. So of course there are different types of nozzles: convergent nozzle, divergent nozzle, convergent divergent nozzle, right? So this is the cross section of a nozzle. If you see, this is the entrance part of nozzle or inlet part of nozzle, and this is the exit part of nozzle. This is the exit part and this is the entrance part of nozzle. Now, when the cross section of nozzle, right, this is the cross section of nozzle, right, decrease continuously from entrance to exit. If you see the cross section here, the entrance to exit, the cross section of nozzle decreases. So this is called convergent nozzle, right? And the smaller section of this nozzle, this smaller part, this smaller section is also called throat. This is also called throat, right? Now, if the cross section of nozzle increase continuously from entrance to exit, this is called divergent nozzle. Now here in divergent nozzle, the smaller section is the entrance section. So this is called throat. The smallest section of the nozzle is called throat. Now if you join this convergent and divergent, right? So this is called convergent divergent nozzle. If you see, when the cross section of nozzle first decreases from entrance to throat, this is called throat section, and then increases from throat to exit section, then it is called convergent divergent nozzle. And this type of nozzle is widely used in various types of steam turbines. So this is already I have told, the smallest section of the nozzle is called throat. So these are the various types of steam nozzles. Now, what is the flow of steam through the nozzle? The steam flow through the nozzle may be assumed as isentropic. Remember, the flow we are assuming, the steam is flowing through the nozzle, right? And the flow that we are assuming is called, we are assuming that called isentropic flow, or that is called reversible adiabatic. That is called reversible and adiabatic, or it is called as isentropic flow. Since During the expansion of steam in the nozzle, neither any heat is supplied nor rejected any work. However, is performed by increasing the kinetic energy of steam. So we have to calculate the flow of nozzle. So before we have to calculate the flow of steam through the nozzle, we should know what is nozzle efficiency, right? So when the steam flows through the nozzle, definitely there will be some loss in the enthalpy or total heat drop takes place due to the friction, right, between the nozzle surface and the flowing of steam. And this can be best explained through this HS diagram, enthalpy entropy diagram, or that is called Mollier chart. Now let us draw a Mollier chart. If you see the when the steam is passing through the nozzle, definitely there will be a pressure drop or enthalpy drop in the steam due to the friction between nozzle surface and the flow of steam, right? So this is the HS diagram, enthalpy and entropy. If you see there is a this is a pressure line, definitely there will be pressure drop. Now first of all, look at the point A, initial point of this steam. So let's say this is point A, right? Where the saturation line meets the initial pressure. This is called P1, initial pressure P1. Right. Now draw a vertical line. Right. Now draw a vertical line through this point A to meet the final pressure. Here it is a vertical line. If you draw, this is the final pressure P2. Here it is a P2. Right. So and meet the final pressure here and to this line P2. Right. And this is done as the flow through the nozzle is isentropic because we are assuming the isentropic flow. So isentropic flow means the entropy here remains constant. That means SA is equal to SB. The entropy of steam remains constant. We are assuming the isentropic flow, right? Which is expressed by the vertical line. Already we expressed this AB. Let's say name this A point and this is B point, and this AB is isentropic flow. Now, what is the heat drop? Now, at this point A, the corresponding line, if you draw, this is called enthalpy line H1, and here it is the enthalpy line H2. So the heat drop, that means the difference between H1 minus H2, the heat drop, is known as the isentropic heat drop. This is called isentropic heat drop. That is called AB. This is called isentropic heat drop. Now, due to friction in the nozzle, what is the actual heat drop? So, due to friction in the nozzle, the actual heat drop in the steam will be less than this isentropic heat drop, right? Definitely will be less. So, let this heat drop at shown in this dotted line as B dash. If you draw this line here, so here there is a C. So AC, this is actual heat drop, and this corresponding line will give enthalpy H3. So now, as the expansion of steam ends at pressure P2, therefore final condition of steam is obtained by drawing this horizontal line through C to meet the final pressure at line B dash. Right? Now, the actual expansion of steam in the nozzle is expressed by the curve AB dash. So this is the actual expansion and this is the ideal expansion or isentropic expansion, right? Now, this actual expansion of heat drop, that is nothing but that will be equal to H1 minus H3. This is called actual heat drop. Now, the ratio of this actual heat drop to the isentropic heat drop will give the nozzle efficiency. This is how to calculate the nozzle efficiency. So the coefficient of nozzle, or that is called nozzle efficiency, coefficient of nozzle, or that is called nozzle efficiency, is defined as the ratio of actual heat drop or useful heat drop to the isentropic heat drop. If you write in mathematically, what is the actual heat drop? H1 minus H3. What is the isentropic heat drop? H1 minus H2. So this will give the nozzle efficiency, which is denoted by the symbol capital K. This is how to calculate the nozzle efficiency. Next, what is the flow of velocity through the nozzle? Now that we are going to calculate. Consider a unit mass of nozzle. So unit mass of flowing steam passing through a nozzle. Let this capital V1, the velocity of steam at the entrance in the nozzle. V2, the velocity of steam at any cross section. Because we don't know, we are calculating for a convergent nozzle or divergent nozzle or convergent divergent nozzle. In general, we are calculating what is the velocity of steam which is passing through the nozzle, steam nozzles. Now, you take V2, the velocity of steam at any cross sections. Let H1 is the enthalpy or total heat of steam entering into the nozzle or at the entrance of the nozzle, that is called H1, and H2 is the enthalpy of steam is passing through the nozzle or after passing through, that is exit, that is called H2. Let us apply steady flow energy balance equation to a steam nozzle. Steady flow energy balance equation to a steam nozzle. So what is the steady flow energy balance equation? M dot mass flow rate H1 plus kinetic energy plus potential energy plus rate of heat transfer is equal to M dot H2 plus V2 square by 2 plus potential energy plus rate of work transfer. So when we are applying the steady flow energy equation, this is the steady flow energy equation, right? Now we are applying to the nozzle. So we are considering the unit mass. Unit mass means this will becomes unit. So this will becomes 1 kg per second. 1 kg per second. This is the kinetic energy. This is potential energy, heat transfer and work transfer. By neglecting the kinetic energy, potential energy, heat transfer and work transfer, the final equation becomes H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. So this is what it is written here. The energy balance equation. By neglecting the losses, definitely there will be a loss. So by neglecting the losses, this loss part will be neglected. Now if you ask questions why it is here divided 1000, this will be divided 1000 because it will convert to kilojoule per kg. Whatever unit will become, it will becomes kilojoule per kg. Because V is in meter per second. But convert to whatever the answer is coming for enthalpy, it will be joule per kg. But to convert to kilojoule per kg. So by neglecting the loss in the nozzle, we have to calculate what is the exit velocity or velocity of steam flowing through the nozzle. What is the exit velocity? That is called V2. From this equation, calculate V2. So this will becomes under root V1 square into 2000 will be H1 minus H2. Or let's say this H1 minus H2 will be HD. And HD is known as the enthalpy of heat drop during the expansion of steam in the nozzle. So that is called H1 minus H2. This is HD. So the exit velocity becomes V2 is equal to V1 square plus 2000 HD under root. Right. Now what is this 2000 that we will calculate? Since the entrance velocity of the steam or velocity of approach, that is called V1, is negligible as compared to V2. Now this here equation becomes V2 is equal to under root 2000. If you see here, this V1 will be neglected. Then what is the V2? V2 is equal to under root 2000 HD. If you calculate this under root 2000, it becomes 44.72 under root HD. But remember, in actual practice, there is always a certain amount of friction present between the steam and the nozzle surface. This will reduce the heat drop by 10 to 15%. Thus, the exit velocity, that is V2 of steam, is also reduced correspondingly. And this above relation may be written as this V2 is equal to 44.72 under root kHd. So this is the exit velocity of steam passing through the nozzle, where this K is nothing but the nozzle efficiency or coefficient of nozzle. Let us solve one problem. Excuse me. Dry saturated steam at 5 bar with negligible velocity expands isentropically in a convergent nozzle to a 1 bar and dryness fraction is 0.94. Calculate the velocity of steam leaving the nozzle. What is the velocity of steam? What is the velocity V2 that will left the nozzle? If you see here, the condition of steam is given dry saturated. and the initial pressure is given 5 bar. P1 is given 5 bar with a negligible velocity, right? So V1 will be neglected. Expands isentropically in a convergent nozzle to a pressure of 1 bar. P2 pressure 1 bar, and dryness fraction at x2 0.2 is called 0.95. So definitely we will be using steam table here. Since this is a steam, the property of the refrigerant we are using the nozzle is called steam. So we will use the steam table. So how to calculate this velocity V2? Velocity V2 is nothing but, already we have discussed, 44.72 under root HD, which is nothing but 44.72 under root H1 minus H2, right? So how to calculate H1 and H2? And this will be calculated from steam tables. Now the initial condition of steam is given pressure P1 5 bar, and one more data is given, X1 is 1. Dryness, it is called dry saturated steam. So dryness fraction will be 1. So from steam table, H1 is equal to HF plus X into Hg minus HF, right? If you will put here 1, X is equal to 1. So this HF will be cancelled, and this will becomes Hg, right? So at pressure 5 bar from steam table, what is the value of Hg? That will becomes 2747.5 kilojoule per kg. So this will becomes H1. This is how to calculate H1. How to next? In a similar fashion, you calculate what is H2. H2 is equal to HF plus X into HFG. So HF at pressure 1 bar, HFG at pressure 1 bar. You calculate from pressure 1 bar what is HF, what is HFG. Now what is the dryness fraction? Then you put it here. What is the dryness? What is the value of HF? 417.5. Dryness fraction is 0.94 into HFG. So you will get the value of H2. Then you calculate the exit velocity of steam leaving the nozzle. Exit velocity, that is called V2. So V2 is equal to 44.72 under root H1 minus H2. Right? So this is the value of H1 and this is the value of H2. Calculate, find out the value of velocity V2. So this is how to solve the problems. Next question. Dry saturated steam at a pressure of 15 bar enters in a steam nozzle and discharged at a pressure of 1.5 bar. So the initial condition of steam is given, again dry saturated steam. That means your dryness fraction initial condition 1, pressure P1 is equal to given 15 bar, right? And discharge at a pressure of 1.5 bar. So P2 is equal to 1.5 bar. Calculate the final velocity of steam. That means what is the velocity V2 that you have to calculate when the initial velocity is negligible, right? If the 10% of heat drop is lost in the friction, what is the percentage reduction in the final velocity? First we have to calculate what is velocity V2. Then after considering the total 10% of heat drop in the friction, we are again calculating what is the exit velocity. Then you have to calculate the percentage reduction. What is the percentage reduction in the final velocity, right? So from steam table, at pressure 15 bar and dryness fraction 1, that means it will becomes only Hg at pressure 15 bar. At pressure 15 bar, from steam table we see what is the value of Hg. That will becomes H1, right? So at pressure 1.5 bar, and again here it is also the enthalpy of condition of steam is dry saturated at exit. So that also becomes Hg, and but that pressure is called 5 bar, sorry 1.5 bar exit pressure. Then you calculate what is the difference between enthalpy one entrance and what is the enthalpy at exit. That is called heat drop. Then you calculate what is velocity V2. So 44.72 into under root HD. So this will becomes V2, velocity V2, final velocity of steam. If you consider the 10% of heat drop will be lost in the friction, then what is the nozzle efficiency? How much? So this will becomes 100 minus 10. So that will becomes 90%. So nozzle efficiency will be nothing but 0.9. Right. Then what is the velocity V2? When you are considering the nozzle efficiency, 44.72 under root K HD. This is nothing but H1 minus H2. Then we will got the value of V2 after considering the nozzle efficiency. Then what is the percentage reduction? The exit velocity without efficiency, the exit velocity with efficiency. Divided by without efficiency, we got the percentage reduction in the final velocity of steam. Next, we have to calculate what is the mass of steam discharged through the nozzle. We have already discussed that the flow of steam flowing through the nozzle is isentropic. We are considering the flow, or we are assuming the flow is to be isentropic, or it is called reversible and adiabatic process, which is given by the law already we know, PV to the power n is equal to constant for polytropic process, right? Where n is called isentropic index. Isentropic index. PV to the power n is equal to constant. So what is the gain in kinetic energy? That will becomes V1 square by 2 plus V2 square by 2. Right? This is the gain in kinetic energy. By neglecting, if you neglect the initial velocity of steam, so it will becomes V2 square by 2. So what is the total heat drop? The total heat drop is nothing but the entire work done during the Rankine cycle. That already we calculated in thermodynamics. What is the work done for a process PV to the power n is equal to constant? That is nothing but the polytropic process. That equal to n by n minus 1 P1 V1 minus P2 V2. This is the work done during the Rankine cycle, or it is called heat drop in the Rankine cycle. Since the gain in kinetic energy will be equal to the heat drop, therefore we'll equate these two equations. V2 square by 2 is equal to n by n minus 1 P1 V1 minus P2 V2. If you see here n by n minus 1, you take this P1 V1 taking outside the bracket. So it will becomes 1 minus P2 by P2 V2 by P1 V1. Right? This is equation number 1. Already we know the law PV to the power n is equal to constant. So that means it is P1 V1 to the power n, that it will equal to P2 V2 to the power n. So what is V2 by V1 to the power n? V2 by V1, that is equal to P1 by P2. Right? So what is V2 by V1 to the power n? Equal to P2 P1 by P2 to the power 1 by n. If you just writing the reverse, V2 by V1 is equal to P2 by P1 to the power minus 1 by n. So what is V2? V1 into P2 by P1 to the power minus 1 by n. Now substitute this value of V2 by V1 in equation 1. Here there is a term V2 by V1, right? We have to substitute the value of V2 by V1 in this equation 1. What we will get? V2 square by 2 is equal to n by n minus 1 into P1 V1, 1 minus P2 by P1. Instead of this V2 by V1, you write V1 P2 by P1 to the power minus 1 by n. Right? Now the base will be same. The base same means the power will be added, right? So this will becomes n by n minus 1 P1 V1 1 minus, if you added this power P2 by P1, this will becomes n to the power n minus 1 by n. Then what is V2? So V2 square, V2 is equal to under root 2 into this n by n minus 1 into P1 V1 into 1 minus P2 by P1 to the power n minus 1 by n. This is equation number 3. This is the exit velocity of the steam leaving the nozzle. This is the velocity of steam leaving the nozzle, V2. Right? But our aim is to calculate what is the mass of steam which is passing through the nozzle. Now, the volume of steam flowing for the second. What is the volume? How to calculate the volume of steam? The cross-sectional area of nozzle into velocity of steam. That will be nothing but area into velocity V2. So what is the volume of 1 kg of steam? That is specific volume of steam at pressure P2. Let's say this is small V2, meter cube per kg. So how to calculate mass? So mass is equal to volume of steam flowing per second, that equal to area into velocity V2 divided by what is the volume of 1 kg of steam at pressure P2, which is nothing but the specific volume V2. So M is equal to mass is equal to A V2 by small v2. This is area by volume, specific volume V2. Already we know the velocity V2 from equation 3. Now substitute here. So A by V2 under root 2 into n by n minus 1 P1 V1 whole into 1 minus V2 by P1 to the power n minus 1 by n. Now if you solve these equations, substitute the value of V2 here. If you see, already we know the value of specific volume V2 from this equation 2. What is that? V1 into P2 by P1 minus to the power minus 1 by n. Now substitute here instead of V2. So we'll get A by V1 P1 by P2 to the power minus 1 by n under root 2n by n minus 1 into P1 V1 to the power 1 minus P2 by P1 to the n minus 1 by n. Now if you solve this equation, you will get this. Finally, you reach this equation. Area under root 2n by n minus 1 into P1 by V1 whole into P2 by P1 to the power 2 by n minus P2 by P1 to the power n plus 1 by n. So this is equation number 4. So this equation is important. How to calculate the mass? This is the mass of steam flowing through the nozzle. So now using these relations, we'll solve one problem. The question is, dry air at a temperature of 27 degrees Celsius at a pressure of 20 bar enters a nozzle and leaves at a pressure of 4 bar. Right. Calculate the mass of air discharged if the area of nozzle is 200 millimeter square. What is the initial condition of steam? Dry air. What is the where the refrigerant is used? Air, right? But the temperature of air, initial temperature T1 is equal to 27 degrees Celsius. Convert to Kelvin. This will becomes 300 Kelvin plus 273 add it. And pressure P1 is equal to 20 bar. Enters a nozzle, right? This is the initial conditions. And leaves at a pressure of P2 is equal to 4 bar. Right? What is the mass of air discharge? M. If the area of nozzle will be 200 millimeter square. So that will becomes 200 into 10 to the power minus 6 meter square. Because 1 millimeter is 10 to the power minus 3 meter. Already we know mass M from equation number 4, right? That equal to A under root 2n by n minus 1 into P1 B1 to the power P2 by P1 whole into P2 by P1 to the power 2 by n minus P1 2 by P1 to the power n plus 1 by n. What is the n? Isentropic index. And the refrigerant is given air, right? For air, isentropic index will be 1.4. So substitute here the value of area 200 into 10 to the power minus 6. 2 into n is 1.4 and pressure P1. This is given 20 bar. So 20 into 10 to the power 5 Newton per meter square. And this will be becomes 4 into 10 to the power 5 Newton per meter square, or we can call it as Pascal. Substitute here. We will get the value of mass. That will become 0.72 kg per second. This is how to calculate the mass of steam discharged through the nozzle. Next, what is the condition for maximum discharge through a nozzle? Or that is, we call it as critical pressure ratio. If you see the equation, this nozzle, mass of steam discharged through the nozzle, there is a term called P2 by P1. The term is there, P2 by P1, right? This term. So this term will be called as critical pressure ratio. Critical pressure ratio. Critical pressure ratio. So, what is the condition of this maximum discharge? that will depends on this critical pressure ratio. How to calculate the condition for maximum discharge, right? See, it is obvious from this equation we have what I have seen that there is only one value of the ratio that is called critical pressure ratio P2 by P1. Already I told, which will produce the maximum discharge, and this can be obtained by differentiating the mass equation number 4, mass equation, with respect to this P2 by P1 and equating to the 0. What is the in that equation? If you see in equation number 4, P2 by P1 to the power 2 by n, 2 by n. This is P2 by P1 to the power 2 by n minus P2 by P1 to the power n plus 1 by n. To get the maximum discharge, we will differentiate this equation with respect to P2 by P1. If we differentiate, this will becomes 2 by 2 n to the power P2 by P1 to the power 2 by n minus 1 minus n plus 1 by n into P2 by P1 to the power n plus 1 by n minus 1 and equating into 0. Then from this equation we will calculate what is P2 by P1, what is the value of P2 by P1. Let us calculate here. So this will becomes P2 by P1 will becomes 2 by n plus 1 to the power n by n minus 1. So this is the condition for maximum discharge, which is nothing, sorry, this is P2 by P1, which is nothing but the critical pressure ratio. The ratio of this P2 by P1, already I told, is known as the critical pressure ratio, and this pressure P2 at the throat is known as the critical pressure. The maximum value of discharge flowing per second is obtained by substituting. After we will get this value of critical pressure ratio. This is the condition for maximum discharge. To find out the maximum, what is the maximum discharge flowing per second, we have to calculate by substituting this P2 by P1 in equation number 4. If you see this equation here, in place of this P2 by P1, we substitute the value of this critical pressure ratio. Then we will calculate what is the value of mass. This is the maximum discharge. If we substitute, this is called maximum discharge. So that will becomes 2 by n in place of P2 by P1, P2 by P1 that equal to 2 by n plus 1 to the power 2 by n minus 1. So we substitute instead of P2 by P1. Then we calculate the maximum discharge, and this will become a under root 2n by n plus 1 into P1 B1 to the power whole into 2 by n plus 1 to the power 2 by n minus 1. Sorry, here it is n by n minus 1. So this is the maximum discharge flowing through the nozzle per second. Now what is the values for maximum discharge through a nozzle? As I told, the steam, the condition of steam, it may be dry saturated, it may be superheated, or it may be a gas. So for dry saturated, the value of n is 1.135. This is for superheated, n is equal to 1.3, and for gas, n is equal to 1.4. What we called call it as air, or we consider as air for gas. If you see in this equation, a maximum mass is equal to under root 2n by n plus 1 into P1 B1 to the power whole into 2 by n plus 1 to the power 2 by n minus 1. So for different condition of steam, we substitute the value of n. For dry saturated steam, the n value is 1.135. If you put the value of n is equal to 1.135, we will get the value of this answer. The maximum mass will be equal to 0.637 into area under root P1 by V1. This is for dry saturated steam. If you put the value of n 1.3, you will get the maximum value of discharge is 0.666 A under root P1 by V1. For gas or air, you put n is equal to 1.4. You will get the maximum value of mass discharge flowing per second is 0.685 into area under root P1 by V1. Now the question is, dry air at a pressure of 12 bar and temperature 600 degrees Celsius. The refrigerant we are using, that is called air. That means your n is equal to 1.4 The initial pressure P1 is given 12 bar and the temperature T1 is given 300 degrees Celsius. Is expanded isentropically through a nozzle at a pressure of 2 bar. So P2 is equal to 2 bar. Determine the maximum discharge through the nozzle of area is equal to 150 millimeter square. Right. So already we know, since it is a air, what is the maximum discharge? The maximum discharge will be equal to 0.685 into A under root P1 by V1. This area is given 150 millimeter square. P1 is given. What is the volume V1? How to calculate? We are using air, right? This is a gas. We are using the gas equations. PV, P1, V1, PV is equal to MRT. That means P1, V1 is equal to MRT1. So what is V1? MRT1 by P1, calculate V1 and substitute the value of P1 and V1 here and area. You calculate the maximum mass. That will become 0.304 kg per second. What is the speed of sound? When the steam is flowing through the nozzle, definitely there will be a disturbance, right? Due to the disturbance, there is a there will be a speed. Definitely, when the steam is flowing through the nozzle, how much velocity of steam it will flowing through the nozzle? There will be disturbance, right? So an important parameter in the study of compressible flow is called the speed of sound. What is the speed of sound? Or that is called sonic speed, which is the speed at which infinitely small pressure wave travels through a medium. The pressure wave may be caused by a small disturbance, which creates a slight rise in the local pressure. Right? Now, to obtain a relation between the speed of sound in a medium, let us consider a pipe. So this is a pipe fitted with this piston. This is called piston. This is called piston. And let us consider that fluid is at rest conditions. Right. Now a piston fitted in the pipe is now moved to the right. Here piston is there, we'll apply force here, right? F. Now this piston will move to right with a constant increment in velocity dv, change in velocity. When the piston moves to the right, it will create a sonic wave, right? And that this wave front moves to the right through a fluid at the speed of sound c. Let's say the speed of sound is c. The speed of sound is called c. And separate the moving fluid adjacent to the piston from the fluid still at rest, right? The fluid to the left, if you see the fluid to the left of the wave front experience an increment in its thermodynamic properties, while the fluid on the right of the wave front maintains its same original thermodynamic properties. Right? Let us consider in the left side of the properties of fluid. Let's say this is enthalpy H, pressure P, and density rho. Now, to simplify this analysis, consider a control volume. Let's say this is a pipe, this is a wave front. Let this wave front as a whole control volume traveling with this wave front. Right? Consider a control volume that encloses the wave front and moving with it. To an observer, if you see the observer, while traveling with the wave front, the fluid to the right will appear to moving towards the wave front with the speed of sound c, and the fluid to the left, this is the speed of sound, and fluid to the left moving from the wave front with a change in velocity that is called c minus dv. Now we'll apply the mass balance equation to this left and right combinations. So what are the mass in and what are the mass out? What are the mass in here? That is equal to rho density a into velocity c. Since we are considering the speed of sound is c, that is equal to what is the change in properties when this wave front is moving left to the right? The change in thermodynamic property will be, let's say here it is initially enthalpy, pressure, and density. What is the change in enthalpy? H plus ds, pressure, P plus ds, density, rho plus d rho. Now what is the mass to the left? So rho means rho plus d rho, area will be remains constant, into c minus dv, change in velocity. By neglecting the higher order term, if you multiply these, the higher order term will be coming. So this will becomes rho AC, let's say this is rho AC minus rho dv, rho dv into a, rho dv into a, this is rho AC minus rho dv into a plus a d rho, rho a, plus a d rho, yes, a d rho c minus a d rho into dc. So by neglecting the higher order terms, this equation will reduce to c d rho minus rho dv is equal to 0. This is equation number 1. We will get this from this. And this will be cancelled. Right? So this is the first equation. Then apply, this is the mass balance equation. Now we will apply the steady flow energy balance equation to this nozzle. So what is that? H plus c square by 2 kinetic energy. This is the equation writing by neglecting the kinetic energy, potential energy, heat transfer and work transfer. So in the left conditions, H plus c square by 2. This is the kinetic energy. This is equal to what is the change in enthalpy? H plus dh plus change in velocity c minus dv to the power square by 2. This is the steady flow energy equations. If you open that square bracket, c square plus dv square minus 2c dv. By neglecting the higher order terms dv square, you will get this equation. dh minus c dv is equal to 0. Right? This is equation number 2. And we know that h is equal to u plus pv. Right? And what is dh? It is equal to du plus pdv plus vdp. What is du plus pdv? That is nothing but this pdv is equal to work transfer. So du plus dw, that is equal to nothing but dq plus vdp. What is dq? tds plus vdp. So what is tds? dh, sorry. So dh will be nothing but tds plus vdp. That equal to tds plus dp, dp. What is specific volume? That is called the reciprocal of density, dp by rho. What will become this? tds is equal to dh minus dp by rho. What is tds? This tds is equal to dh minus dp by rho. This equation. And we are considering the isentropic process. So this tds is equal to 0. So now this will become 0. So dh is equal to dp by d rho. dp by rho. This is equation number 3. Now combining these 1, 2 and 3 equations, this will gives the speed of sound. That will become c square is equal to dp by d rho at constant entropy, because we are considering the isentropic process. So we can write this c square is equal to del p by del rho at c square is equal to, we can write it here, del p by del rho at constant entropy process. Right? Or we can write c square is equal to k into del p by del rho at constant temperature from the Maxwell's relations, where this k is called the specific heat ratio of the fluid. That is nothing but that equal to Cp by Cv, specific heat ratio, K. Again, we know that from ideal gas equation, Pv is equal to mRT. That will becomes m by v at T, that equal to m mass by volume rho RT. So P is equal to rho RT. So here instead of P, you write down rho RT. C square is equal to K del by del rho of rho RT. And if you differentiate a partial differentiation, this will be constant RT. So this will becomes 1. So this will becomes KRT. So C square is equal to KRT, right? But C is equal to under root KRT. This is how to calculate the speed of sound. Here, what is capital R? The characteristic gas constant, and it has a fixed value for a specific ideal gas and the specific heat ratio of an ideal gas or a function of temperatures. So this is how to calculate the speed of sound. Now the most important parameters where the speed of sound depends, that is called Mach number. What is the Mach number? Mach number is the ratio of actual velocity of fluid, or that is called an object in the air, to the speed of sound at the same fluid at the same state. That is, Mach number is equal to the velocity of fluid by the speed of sound. That is called Mach number, right? And the Mach number depends on the speed of sound, which depends on the states of the fluid. And these fluid flow regimes are often described in terms of the flow, that is called Mach number. Now, when this Mach number Ma is equal to 1, this is called sonic flow. If it is less than 1, it is called subsonic. Greater than 1, it is called supersonic flow. So we have three types of flows: sonic flow, subsonic flow, and supersonic flow. If the Mach number is equal to 1, sonic flow, less than 1, subsonic flow, and greater than 1, supersonic flow. Let us solve one problem. Air enters a diffuser with a velocity of 200 meter per second, right? So velocity is given 200 meter per second. Calculate what is the speed of sound, that is called C, and what is the Mach number, Ma. Also, at diffuser inlet, when the temperature of air, inlet temperature of air is given, that is equal to T, 30 degrees Celsius. So after calculating the speed of sound and Mach number, what is the type of fluid flow, whether it is sonic or subsonic or supersonic, that you have to identify. Now if you see here, the velocity is given 200 meter per second, Mach number is temperature is given. So what is the speed of sound, that is equal to under root KRT. Right? What is K? Specific heat ratio. We have called it as air. We have taken here air. This is 1.4. Right? What is the value of R for air? That is called characteristic gas constant. So characteristic gas constant is equal to 0.287 kilojoule per kg Kelvin. Right? This is called characteristic gas constant. What is universal gas constant, RU? That is called characteristic gas constant by molecular mass. Sorry. The characteristic gas constant is equal to universal gas constant divided by the molecular mass. This is how to calculate the characteristic gas constant. And this universal gas constant is the value is 8.314. Substitute here R value 0.287, and the temperature is given 20 degrees Celsius, 30 degrees Celsius, convert to Kelvin. And when we are calculating this speed of sound, we see the units. Here it is in kilojoule per kg, it is in Kelvin, and multiply 1000 to convert to joule. So it will becomes 349 meter per second. This is the speed of sound. So after calculating the speed of sound, what is Mach number? Velocity by speed of sound, that it will becomes 200 by 349. It will becomes 0.573. So it will be less than 1, right? So if it is equal to 1, this is called sonic flow. Less than 1, subsonic flow. Greater than 1, supersonic flow. Now it is less than 1. So it is the type of flow is subsonic. So this is all about speed of sound and Mach number. Now let us consider one more problem. Air is expanded reversibly and adiabatically in a nozzle from pressure 13 bar and temperature 150 degrees Celsius. The medium is given air, and this is expanded reversibly and adiabatically. Here it is called isentropic process. Isentropic flow. This is called isentropic flow, right? At a pressure of initial pressure is given 13 bar and temperature 150 degrees Celsius to a pressure of 6 bar P2. The initial velocity of nozzle is very small. That means we are neglecting V1, initial velocity of steam. The process occurs under steady flow conditions. Calculate the exit velocity of the nozzle V2. Definitely, when we are considering the steam nozzle, remember where there is some assumptions. We are neglecting the initial velocity. We are assuming the flow is to be isentropic or reversible and adiabatic, and the flow conditions to be steady state. It will be steady state. Now, pressure P1, temperature T1, pressure P2, velocity V1 is 0. We have to calculate the velocity V2. We will apply the energy balance equation at cross section 1 and 2. So what is that? H1 plus V1 square by 2 plus potential energy plus heat transfer is equal to H2 plus V2 square by 2 plus potential work transfer, right? Now we are neglecting the potential energy, heat transfer, initial velocity of steam already given 0. So kinetic energy will be neglected at inlet at cross section 1. Potential energy at outlet 0 or transfer 0. So this equation will becomes H1 is equal to H2 plus V2 square by 2. This is the equation. Right? H1 is equal to H2 plus V2 square by 2. We have to calculate what is V2 from that equation. So V2 is equal to, what is that V2? That is called 2 into H1 minus H2 under root. So how to calculate H1 and H2? Already we know Cp is equal to H by dt. So what is dH? Cp into dt. So this will be equal to, what is H? Cp into T1. 2 into, so this is Cp T1 minus Cp T2 under root, right? So this will becomes 2 into Cp T1 minus T2. Already we know the value of Cp for air. What is the value of Cp for air? 1.005 kilojoule per kg Kelvin. Cv is equal to 0.718 kilojoule per kg Kelvin. Temperature T1 is given in that equation 150 degrees Celsius. But how to calculate T2? Since we are assuming the ideal gas equations, the flow is isentropic between 1 and 2, right? Since it is isentropic flow, so temperature will apply the thermodynamic relations. T2 by T1 will be equal to P2 by P1 to the power n minus 1 by n, where n is 1.4 for air. From this equation, you calculate what is the value of T2 that you have calculated. This one. So after calculating T2, calculate the value of V2, velocity V2. This is the exit velocity of the nozzle. This is how to solve the problem. Next, steam having pressure of 10.5 bar and 0.95 dryness is expanded through a convergent divergent nozzle, right? The nozzle is given convergent and divergent, right? And the pressure of steam leaving the nozzle is 0.8 bar. Calculate the velocity at the throat for maximum discharge conditions, and index of expansion is given 1.135. Also calculate the mass flow rate of steam passing through the nozzle. Now if you see, the nozzle is given convergent divergent, right? This is the nozzle, convergent divergent. This is 1, 2, exit, and this is called 3, throat. Here the pressure is given 10.5 bar and exit pressure is given 0.85 bar. What is the throat pressure we have to calculate? The condition is given, calculate the velocity at the throat. That means V3. Here we have to calculate the velocity V3. What is the velocity of V3? Throat for maximum discharge conditions. We know for maximum discharge, P2 by P1 is equal to 2 by n plus 1 to the power n by n minus 1. From that you calculate what is P2. This is the throat pressure. This is the throat pressure. Sorry, according to the problems, here it is 3 exit velocity and this is the throat at 2, cross section 2. So this is the throat pressure you have to calculate, P2. So after calculating P2, what is the maximum velocity you have to calculate? For maximum discharge conditions, V2 is equal to under root 2 into n by n plus 1 P1 V1. Calculate the value of V2. This is the value of V2 that we got. Right? Next, what is the mass flow rate? How to calculate mass flow rate? After knowing the velocity of V2, the mass flow rate is equal to A2 V2 by small v2. We have to calculate the mass flow rate per unit area, per unit kg of area, right? So this is 1. It's already how to calculate the volume V2. Already we know PV to the power n is equal to constant. So P1 V1 to the power n is equal to P2 V2 to the power n, right? From this equation, you calculate. When you know P1, you know P2. And what is the value of V2? Sorry, V1. How to calculate? So V1 is equal to, here it is given dryness fraction 0.95. 0.95 into what is the value of Vf at pressure point 10.5. So from steam table, calculate what is the value of Vf at pressure 10.5 bar. This is the value 0.185. So substitute here to the power n. From this equation, you calculate what is V2. Then you will calculate what is the mass flow rate. Then you calculate the mass flow rate, that equal to area into V2 by small v2. So you will get the answer. Value of mass flow rate is equal to 1544 54.4 kg per meter square, because we have taken here unit area. So this is how to solve the problems based on steam tables and steam nozzles. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.